Okay, I think it's time to start one more lecture of our P&S in processing in memory. And tomorrow we are going to cover very interesting work that we published this year at ASPLOS 2000. 1 second, please. I'm listening to myself. So yes, this is something we published this year in ASPLOS 2021. I think it's kind of a very interesting and very complete framework to implement different types of operations using DRAM. And essentially, we are, through this project, enabling a way of using DRAM as a very large SIMD machine. So that's the title of today's lecture, Bit Serial SIMD Processing Using DRAM. And before we go into the details of the Sindiram project itself, which is this framework that enables SIMD processing using DRAM, let me give you a little bit of context. So this is something that you all have already seen multiple times over the course of this course, and also other presentations from our group, from Professor Mudlu. This is the ABMEM processing in DRAM engine that consists of ABMEM DIMMs. Each of them has multiple chips, and in these chips we have, near the memory arrays, we have some small processors called DPUs. We also discuss in this course this other approach to processing near memory that is called Samsung FinDRAM. It's based on HBM2 memory, as you may remember, and inside an HBM stack we may have some dies, some of the layers that are for storage, and some others that are for compute. And here you can see the layout of some of these, of one of these compute layers, where we can identify the cell arrays or the banks, and how each of the banks, or how every two banks are connected to a PCU block, which is essentially a SIMD unit that has access to the two neighboring or adjacent banks. And we also discussed and presented this other implementation and DIMM-based processing in memory system from Samsung as well, where on each of the DIMMs we can place some type of processor or processing element, in this case called AX DIMM buffer. But you may remember that this has been implemented in a prototype using an FPGA and tested with recommendation systems. And all these approaches that already exist in reality, in the real world, are what we call processing near memory. And why is that? Because in the end, the computation itself is happening near the memory array. We have DRAM subarrays, or we have DRAM banks, or we have DRAM ranks, as in the case of AXDIMM, and we place the compute units or the processing elements near these memory spaces. And that's why we call them processing near memory. But in the beginning, when we started this course, and also in some other lectures, when we talk about real world processing in memory systems, we also talk about another approach to processing in memory that is called processing using memory. You may remember this. We are going to recap on this, and we are going to talk during the whole lecture about processing using memory today. So processing using memory essentially consists of taking advantage of the way that the memory cells work, and in order to perform some sort of computation, maybe some data movement or a row copy, for example, or maybe some bitwise operations. Those are the things that we discussed in previous lectures. And we are going to start from there today. If you want to read more about this classification, processing near memory, processing using memory, I can recommend you our book chapter. There you will find this kind of taxonomy that groups the PIN approaches into two different approaches, processing using memory and processing near memory, and the different technologies that enable these two ways of doing processing in memory. But yeah, now let's talk about processing using memory. As usual, please stop me if you have any questions, guys. And same as usual as well, I will keep an eye on the YouTube chat in case that there are any questions there. So processing using memory, as I said before, and here you have again the definition, it's to take advantage of the operational principles of memory to perform either data movement or some computation inside memory. Good thing of processing using memory is that it can exploit the internal connectivity to move data, and it can also exploit the analog computation capability. This is something that we talk about in previous lectures, as I said, but we are going to recap on these two ways of using memory to move data or to perform some sort of computation inside it, and we will build on top of that. There are some approaches, some examples that we have discussed in previous lectures, like RowClone or Ambit. Those we are going to we are going to recall them today. But yeah, you have here some links to the corresponding papers. And if you want to refresh everything that we covered in previous lectures about processing using memory or processing using DRAM, because actually these approaches that we presented are for DRAM, I can recommend you the first meeting of this course, where we talk about some processing near memory and also some processing using memory approaches, or you can also watch the two lectures that we gave this fall semester in the computer architecture master's course about processing using DRAM. Remember that processing using DRAM might sound like, you know, I don't know, it may be a little bit even futuristic, right? Like having the capacity of performing operations using DRAM itself without modifying it or by modifying it minimally. But we have already seen some work that has shown that these processing using memory operations are feasible even in off-the-shelf DRAM chips. That was the Compute DRAM paper presented at Micro 2019. And there, the authors, by using some FPGA-based memory controllers, SoftMC, you can find a link to a repository where you can download SoftMCs here. By using SoftMC, they were able to emulate the RowClone, which is this figure here on the left, and Ambit as well, which is this right figure here. So essentially what they did was playing with the timing parameters, the latencies that we have to respect between activation and pre-charge commands from the memory controllers, and they were able to emulate, in this case, the copy of one row to another row by reducing these two significantly until a point where the bit line is still charged, and when activated, when the sense amplifier is enabled, this makes that the charge of the bit line goes to the destination cell or the destination row when we have a whole row. So essentially the idea here is to activate one row, in this case the source row R1. When we activate the row, the charge of the cells starts perturbating the bit line, so this makes that the voltage of the bit line increases. At that point, we enable the sense amplifier in this step 2, and then we pre-charge. But after pre-charging and making sure that the charge of the source row is restored, we will start seeing how the charge in the bit line that is indicated by these boxes on top starts decreasing. But at some point, what the authors of Compute DRAM do is issuing or send a new activate command to the DRAM chip from the memory controller before the voltage of the bit line is again at the steady state, which is when its voltage is VDD or half VDD, right? And in that case, if we activate the destination row and we enable the sense amplifier correspondingly, we would be copying the voltage of the bit line to the destination cell. So that's essentially how they made this RowClone emulation. For Ambit, they kind of followed a similar idea, also reducing these T1 and T2, which are the latencies between activation and pre-charge, and between pre-charge and activation, reducing it, essentially having equal to 0 cycles. And by doing so, they can move from the row address, this 01 that represents row 1, to this row 2, to the row address of the row 2, but in between they also go through R3, which is another row that is also used for the computation. And this is the way, this is the way they manage to activate 3 rows at the same time, and in this way implement bitwise operations like and or. We are going to talk again about this. I mean, the idea of activating 3 rows at the same time in order to perform bulk bitwise operations in DRAM, because that's what was proposed by the Ambit work, and our Sindiram project is built upon the Ambit work. You may also remember as well that I think it was meeting number 6. We had Ataberg presenting the PiDRAM project. PiDRAM is a is a real platform that allows us to implement end-to-end processing using memory techniques. It has hardware and software components, including a customizable memory controller that is in charge of issuing the corresponding commands to the DRAM module. You may remember this. Sorry, you may remember this figure with the PiDRAM workflow. First of all, the user application by interfacing, so interfaces with the OS using system calls, and then the OS can use the library that we created to convey the operation to the hardware. And this is done using a store instruction, because the memory, so the registers that exist in this PUM operation controller are memory mapped. So by using the rocket chip, which is essentially the processor here, the CPU can use a store instruction to load the program on this PUM operations controller, and then the PUM operation controller is in contact or is communicating with this scheduler that will start issuing the corresponding commands to the DRAM module to execute either row copy or bitwise operations. We have implemented this PiDRAM on an FPGA prototype. Here you can identify the FPGA that will implement a single core RISC-V CPU, and here is where we place the DRAM DIMM that we can call compute-enabled DIMM, because by using PiDRAM, we are able to execute operations using DRAM. And yeah, if you want to learn more about the PiDRAM project, I can recommend you this meeting 6 where Ataberg presented it, and you can also take a look at the paper, and you can also download PiDRAM from the repository. It's everything completely publicly available. But now that's the situation that we have. So we have someone or a couple of works, probably more, that propose different ways of doing computation using DRAM. The first paper was row clone that explained how to copy one row to another row inside the same subarray. The second one was Ambit, a way of executing bitwise operations, logic operations inside DRAM by activating 3 rows inside the same subarray at the same time. Then we have seen that these 2 techniques are relatively feasible in DRAM chips. That's what the Compute DRAM paper showed. And we have also shown in PiDRAM a way of integrating these techniques into a real system. But the problem at this point is that even though we see that it's feasible to perform some operations using DRAM, these operations are not complex enough to support many different programs and to be really useful for programmers. So this is why it's important and necessary to come up with a framework that allows us to use DRAM for more complex operations, and also exploit all the available parallelism that we have inside DRAM. So this is why we talk about SIMD processing using DRAM, and it will be bit serial, because as you will see, we have to place data in a different way with a vertical layout in order to make SIMDRAM really efficient and really high throughput. So let's talk about the SIMDRAM project. Let's start with a quick executive summary. as I just said, and you already know, processing using memory architectures can effectively perform bulk bitwise operations, bulk bitwise computation. This includes a row copy and also includes logic operations like AND, OR, and NOT. But these architectures are not widely applicable because they only support a very limited set of operations. They lack flexibility to support new operations. And in the cases where we have seen more complex operations, they have required significant changes to the DRAM subarray. So our goal in this project is to design a processing using DRAM framework that allows efficient implementation of complex operations, provides flexibility to support new desired operations, and also changes the DRAM architecture minimally. So this is Sindiram. It's an end-to-end processing using DRAM framework that provides the programming interface, the ISA, and the hardware support for efficiently computing complex operations, providing the ability to implement new operations as required, and also taking advantage of the massive parallelism that DRAM has and use it as a SIMD engine. As we will see, Sindiram shows very promising results. We will talk about them at the end of the presentation. Very interesting speed ups and energy, increased energy efficiency with respect to CPUs and GPUs, not only for Sindiram specific operations, but also for several real world workloads. So yeah, this is the outline. First of all, I'm going to recap on processing using DRAM. I already did at the beginning of the lecture, but I guess it's fine if we again refresh everyone's with row clone, Ambit, and so on. We are going to see also a little bit of background on how DRAM operates and also these processing using DRAM techniques. Then we will talk about the Sindiram framework. What's the substrate itself, how is the memory used in Sindiram, and how we need to operate to implement new desired operations inside DRAM. Finally, we will talk about system integration and the evaluation. So let's start with processing using DRAM. One thing that you already know is what's the data movement bottleneck. It's a major bottleneck in terms of performance and energy efficiency on processor-centric systems these days. The main reason is that the memory channel is bandwidth limited and power hungry, and recent works have shown that around 60% of the total system energy is spent on data movement. So the idea is to, as you know, and this is what this course is about, is moving computation closer to where the data resides in a way that we can reduce or eliminate the amount of data movement between the processor and DRAM. And among the different techniques or different approaches to processing in memory, we have processing near memory. As I said in the beginning, is when we place the processing elements near the memory array, but not inside it. And then we have processing using memory, where we exploit the analog operation principles of the memory circuitry to perform computation. And this takes advantage of the large internal bandwidth and parallelism that we have inside the memory arrays. You can just think about DRAM subarray that typically has 2 kilobyte or 4 kilobyte or even 8 kilobyte row buffer. So this means probably up to 64K bit lines. And then we also have a bunch of rows, let's say 1024. So that's a lot of parallelism, and it would be great if we can take advantage of all this parallelism to perform computation and all this internal bandwidth. Previous approaches to processing using memory were able to perform bulk bitwise operations like simple logic operations like AND or XOR, and some works also propose ways of doing addition and multiplication. But as I said, they really entail significant changes to the hardware, and in that sense they are not practical. And also these works don't show how to extend the instruction set that the processing using DRAM engine or substrate can provide. So let's start with a little bit of background. First of all, on DRAM, inside the DRAM chip, well, you know that DRAM modules are composed by DRAM chips, and inside each DRAM chip, we have multiple banks. Inside each bank, we have several subarrays that are 2D arrays of DRAM cells, and these DRAM cells are connected by word lines and bit lines. The bit lines end in sense amplifiers, and the whole group of sense amplifiers connected to a subarray is what we call the local row buffer. Now, if we take a closer look at each of the cells, we will see that each DRAM cell is composed by a capacitor and also an access transistor. The capacitor stores certain amount of charge to either represent a 0 or 1. The access transistor gives us access to the content of the capacitor when the word line is activated. And here in this slide, we can quickly recap on how the DRAM cell operates. In the first step, we need to activate the row. We need to activate the corresponding access transistor, and to do that, we raise the word line. In this, this makes that the access transistor allows the charge that is stored in the storage capacitor to go from the capacitor to the bit line. So the capacitor starts losing charge to the bit line, and this causes a perturbation in the voltage of the bit line, as you see. And at that point, we can enable the sense amplifier. When we enable the sense amplifier amplifies the deviation in the bit line, and the capacitor charge gets fully restored. So at this point, we have whatever value is contained in the storage capacitor, either 0 or 1, is now in the sense amplifier as well. And not only in this sense amplifier, but also the rest of sense amplifiers that compose the local row buffer. So that's the point where we can start reading or writing from or to these sense amplifiers. And at some point, when we have read or written whatever we needed, we can close the row by pre-charging the bit line again. So we first lower the word line, then we pre-charge the bit line again to help VDD for the next access, and then we disable the sense amplifier. So this is how DRAM operates, and based on the way that DRAM cells operate, we can implement some interesting operations. The first operation that was proposed in Micro 2013 was row clone in DRAM row copy. So the key idea here is to have one source row. We are only representing a single cell and a single transistor, but this is a whole row that may have up to 64,000 of these cells, and this is the destination row or cell in this case. Each of them has certain charge. This seems to be fully charged, but as you know, these small capacitors are leaking a little bit over time, so that's why we need to refresh them from time to time, and that's why we will probably we will rarely see them completely charged or completely discharged, as the case of the cell in the row B, and they are connected to the same bit line and to the same sense amplifier. So now the row copy command sequence is as follows. It has 3 steps. It essentially needs 3 different commands: activate, activate, and pre-charge. So first of all, we activate the source row by raising the word line, as you know, and this after enabling the sense amplifier makes that the bit line has the voltage of the storage capacitor in the source row. At that point, because the bit line is charged and the sense amplifier is enabled, we can activate the destination row, and this makes that the charge level of the source row that is in the sense amplifier goes to the destination cell in row B in this case, and in this case is completely charging it, as you can see. After that, we can pre-charge the bit line for the next access, and we would be done. But as you see, now we are we have copied the contents of this cell in row A into the row, right? So this is a relatively simple operation, relatively simple idea, as you can see, but very effective and very powerful when it comes to copying bulk amounts of data. or large amounts of data in bulk from one row to another row. The second idea is proposed by Ambit, presented in Micro 2016, and it's based on this triple row activation that implements a majority function. In this case, we don't have only 2 rows. Here we have 3 rows, and these 3 rows contain input data. So here you see that this one looks like charge, this cell is a charge as well, and this one is this charge, the 3 of them connected to the same bit line. And again, we have a sequence of commands to implement this triple row activation and this majority function. The first of the commands is an activate, but it's a special activate command because it activates the 3 rows at the same time. What happens then is that the 3 cells, the 3 capacitors, start leaking their charge to the bit line and perturbating the bit line. And what's going to happen? In the end, the voltage of the bit line is going to be pulled to the majority of A, B, and C. So if this is charge, and this is charge, and this is discharge, in the end, in the bit line, we will end up having a charged bit line. So we will end up having VDD. So the majority of VDD, VDD, and 0 is VDD. If we had 0, 0, and VDD, the resulting charge in the bit line would be 0. So that's essentially the majority function that we use in Ambit to implement and/or operations. And we are going to use much more today in the Sindiram framework in order to implement much more complex operations. So after this majority function happens in the bit line, the values of the 3 cells, because the sense amplifier is enabled and the 3 rows are open, the corresponding contents of the cells of the capacitors are overwritten. So in the end, it's the majority output that goes to the 3 cells, and after that we can close the rows. We can pre-charge the bit lines for the next access. So by using this idea of the triple row activation, we can implement, as I said, and OR. Essentially, an AND operation is the same as a 3-input majority operation where one of the inputs is fixed to 0, and OR operation is a majority operation where one of the 3 inputs is fixed to 1. So this is the way that Ambit implements AND and OR. But to be functionally complete, we not only need AND and OR, we also need NOT, as you know. And there might be different ways of implementing NOT. I'm not saying that the way that the Ambit paper presents is the best one, but at least this is a way, and it's feasible and it's possible to implement. And it consists of placing at least 1 row of dual contact cells. So notice that as opposed to the DRAM cell that I explained in the beginning, or presented in the beginning of the presentation, where we had the capacitor and 1-axis transistor, in this case, we have 2-axis transistors, each of them with its own word line to activate the transistor for whatever we want to do with it. And observe that this access transistor connected to the N word line is not connected to the bit line, but instead is connected to the output of the sense amplifier. So, and the sense amplifier, as you see here, is essentially composed by 2 inverted, two coupled inverters. So whatever voltage value we have here in the bit line will be inverted in this bit line bar output. And we can use this bit line bar output to connect it to the N word line, to the access transistor of this N word line, and eventually charge the capacitor of the dual contact cell. And here you see how this operates. In the initial state, we have a source row, this DRAM cell that we have here, and the DCC is going to be our destination. First of all, we activate the source row. As you see, this moves the charge of the capacitor to the bit line. Then we activate the sense amplifier, we enable the sense amplifier, and next we activate the N word line of the dual contact cell. So what this makes is that in this step 3, when we enable the sense amplifier, the VDD voltage in the bit line turns 0 on the other side of this inverter, and here when we activate the inward line of the dual contact cell, this 0 gets moved, gets copied onto the capacitor. So this is the way of implementing the NOT operation. So now in Ambit we have AND, OR, and NOT. So this is functionally complete. So we can implement, in theory, any complex operation, right? So that's the key idea in Ambit, and we exploit this key idea in Sindiram as well, as you will see. But anyway, in order to summarize about Ambit, remember in the subarray organization, we have the local row buffer composed by the sense amplifiers. Ambit proposes to use only a limited set of designated rows for the triple row activation. Then we have 2 rows that are pre-initialized with 0s and 1s, depending on whether we want to execute AND or. And then we have the rest of the rows are regular data rows where we store the data. So when we want to operate using these designated rows, the first thing to do will be to move the data from the regular rows to the designated rows. And why are they designated? It's because they are connected to a special decoder that is designed to activate 3 rows at the same time. The regular row decoder is not designed for that, because DRAM is not designed for the triple row activation in principle, and because the authors of the Ambit paper wanted to keep the overhead small, they didn't want to replace the whole row decoder with a powerful row decoder that can activate 3 rows at the same time. Instead, they prefer to use a small special decoder that can activate 3 rows at once. And when this bitwise decoder receives some address, this address from the memory controller, this address actually represents the 3 rows that are going to be activated at the same time. And all of this can be done with very little overhead. According to the Ambit paper, less than 1% of the overhead in existing DRAM chips. So now we know the basics of this processing using DRAM, the row clone operation and the Ambit operations. And as I said, now it's a functionally complete set of AND, OR, and NOT. And in principle, we should be able to implement any more complex operations. But that's something that wasn't shown by previous works. Previous works either implement only basic operations like Boolean algebra, which are not widely applicable, or support only a limited set of operations, lacking the flexibility to support new operations, or if the operations are complex as well, like for example, multiplication and addition, there have been some proposals showing how to do that, but with significant changes to DRAM and costly in terms of area and power. So we need a framework that aids the general adoption of processing using memory, processing using DRAM, by implementing complex operations and by providing the flexibility to support new operations. So that's our goal in this project. The goal is to design a processing using memory framework that can efficiently implement complex operations and provide the flexibility to support new desired operations by changing DRAM minimally. And this is SIMD. We are going to start with the key idea in SIMD, an end-to-end processing using DRAM framework, providing a programming interface, an ISA, and the hardware support. The programming interface is what let's say the regular programmer would use to make use of SIMD. The ISA are the extensions that we need to add to the instruction set in order to be able to support new instructions, and then the corresponding hardware support. We need to have an intelligent memory controller or an extended memory controller that is able to understand these new instructions added to the instruction set architecture and send the corresponding commands to DRAM to execute either row copies or either arithmetic bitwise operations like logic or arithmetic operations, as we will see. So these operations can be complex operations executed in DRAM. We are free to implement new arbitrary desired operations, so the framework is flexible and also takes advantage of the massive parallelism that DRAM has. So in the end, we are turning DRAM into a massively parallel SIMD substrate, as you are going to see. And we are going to talk about the substrate itself, about the hardware itself that we are using. Sindiram is based on two key techniques. The first one is to place the data vertically with a vertical data layout, as you see. So instead of using a horizontal layout, which is a common thing in today's systems, instead of placing bytes and words horizontally, we are going to place them vertically. And this way, we are going to have all bits corresponding to the same element in the same bit line. So as you see here, for example, we have 4 different elements, and each of them is in this, all of them are, so all the bits of each of the elements are in the same bit line, and they are in order, as you see, from the most significant bit to the least significant bit. The good thing of doing this is that each of the bit lines now turns into a SIMD lane. So if we have 64,000 bit lines in one DRAM subarray, we have 64,000 SIMD lanes in a DRAM subarray. And this has also additional advantages, not only the parallelism, but also the fact that allows us to shift bits as they are needed. So if you think about the horizontal layout, if you use it, so with a horizontal layout, it's not possible to shift bits corresponding to the same element from one position to the next position. Why is that? Because the bit lines are completely independent and they are not connected to each other. Previous works have proposed hardware extensions to support this shifting across bit lines, but that obviously entails a significant overhead in terms of area. In this case, with the vertical layout, we don't need to worry about shifting from bit line to bit line, because we can just access whatever bit is needed at a certain point in an operation. And if we eventually want to or need to shift bits explicitly, we can use it by copying one row to another row, as we do with row clone. The second technique that Sindiram is based on is the majority-based computation. Remember from the beginning when I explained Ambit that Ambit supports AND, OR, and NOT, which is great because it's a functionally complete set. But the problem is that this AND and OR are based on majority functions. So the way that AND and OR are implemented is by using a majority function. So in the end, in this work, we can take advantage of the fact that the majority plus NOT set is also functionally complete. Instead of using AND, OR, and NOT, we are going to use majority and NOT, which is also functionally complete, and also it's going to provide higher performance, higher throughput, and lower energy consumption in this specific substrate in DRAM, because the native operation in Ambit is not AND or OR. The native operation is the majority operation. So that's one important technique and key idea of SIMDRAM to take advantage of processing using DRAM and also outperform the original Ambit proposal, as you will see. Now we are going to talk about the framework. So now we understand, so far we understand the idea of processing using DRAM, like the bitwise operations, row copy operations. We know what's the substrate. We know that the substrate is using essentially the same subarrays that were proposed by Ambit with this a special row decoder that can activate 3 rows at the same time. And also we know that the substrate is going to support vertical data layout, and also we are going to use the majority and not based logic to implement more complex operations. Now let's see how we implement more complex operations by describing the Sindiram framework itself. We start from a user input, which is the desired operation. We can start from a and or logic, and or not logic, so the and or not representation of the operation. For example, this one. And in the first step, we are going to generate the corresponding majority-based logic. So what this essentially means, and as we will see in the next slide, is that we convert this circuit based on and or and not into a circuit based on majority and not operations. After we have this majority-based logic, we can generate the sequence of DRAM commands that we will need the memory controller to send to DRAM to execute the corresponding operations. And these DRAM commands are the same DRAM commands that row clone and Ambit propose to implement either row copies or majority operations or not operations. So in the end, they are activate and pre-charge commands. And this sequence of commands represents a microprogram. Notice that at the end of the microprogram, we have a special instruction that only the memory controller understands. This is not sent to DRAM. It's the down, or it could be also halt instruction to indicate that this is the end of the microprogram. With this microprogram, we essentially generate the new Sindiram operation. We can store this microprogram in main memory and use it eventually whenever is needed. And because this microprogram essentially represents the new SIMD instruction that we incorporate to the ISA, and we can make available to users, to programmers. So now someone can use this new BBOP new instruction, use it in their code, and then when the CPU is executing this code and finds this new instruction, communicates to the memory controller that this new instruction, this BBOP new has appeared, so that the memory controller loads the corresponding microprogram and starts sending the necessary commands to the DRAM chips in order to execute the operation inside memory or using memory. Okay, any comments or any questions? Okay, let me know if you have any questions. If not, I think we can start discussing the first step. In the first step, as you know already, what we do is generating the majority-based logic from the and or not logic. We can start with an if transformation, right? So we already know that an AND operation is essentially a majority operation where one of the inputs is 0, and OR operation is a majority operation where one of the inputs is 1, and we could come up with a straightforward conversion of the and or not base representation into the majority not base representation. But this would be an optimized circuit, right? Because in the end, we are using the same number of gates as we have in the original representation. So one thing that we do is applying a greedy optimization algorithm that was proposed in DAC 2014 to generate the corresponding and optimized majority-based logic, as you can see in this example. So in this step 1, by using this greedy optimization algorithm, we can generate optimized majority not implementations of the desired operations. And now that we have this majority-based logic, we can create or generate the sequence of DRAM commands that we will need to execute all these majority operations and not operations, and eventually also some row copies that will be needed. So that's the generation of the microprogram. A microprogram is a series of microarchitectural operations, in this case, activate and pre-charge commands that Sindiram uses to execute Sindiram's operations in DRAM. So the goal of this step 2 of the framework is to generate the microprogram that executes the desired Sindiram operation in DRAM. And this step 2 is divided into 2 tasks. in the first task, we allocate DRAM rows to the operands. In the second task, we generate the microprogram. So let's first start with the task 1, allocating DRAM rows to the operands. So the allocation algorithm that we are going to use here considers two constraints that are specific to Sindiram, to processing using DRAM. The first constraint is that there is a limited number of rows reserved for computation. We remember that the Ambit, original Ambit paper proposes are connected to this bitwise decoder 16 so-called designated rows or compute rows. And there are 16 in Ambit, and we still consider 16 in Sindiram. So the number of compute rows is limited. The second constraint is that we are using majority operation, and this majority operation is based on the triple row activation. And as you may remember, when I explained the triple row activation, when we activate 3 rows, the 3 rows end up having the same value. That is the result of the majority operation, right? So we have to take these two constraints into account when we allocate the operands to rows. Here we have a very simple and easy example of how we could do this. And in this allocation algorithm, so we start from very simple circuit. In this case, is just one majority operation that has 3 input operands, A, B, and C in. So this is actually what we use to calculate the carry out of in a bit serial addition. And this is a pretty simple thing because we only have 3 inputs, so we can directly allocate the 3 inputs to 3 of the compute rows, right? So this is essentially what the allocation algorithm does. What we would do is assigning as many inputs as the number of free compute rows we have. If we eventually have more operands, more input operands in our operation, we will have to use some of the data rows to store the operands, and we will copy the operands to the compute rows when they are going to be used. So yeah, after allocating, we can execute this triple row activation. And as you remember, the majority operation is destructive. So all 3 rows contain the same output value. The good thing of this is we can also take advantage of this because we will probably have to use this output several times in our program, right? And we can do it without having to copy or duplicating the output. In this case, we have, let's say, 3 outputs that we can use as we need them in our program. We are going to see with a little bit more detail how this task 1 allocates the DRAM rows to operands. And we are going to start from, I mean, in this case is the full ladder optimized majority inverter graph. So that's the majority not representation of a full ladder. Here we have the 2 input operands, A and B, and we also have the carrying that comes from the previous bit. Remember that here we have a vertical data layout, so we are operating in a bit serial manner, and this full ladder contains, as you see, 3 majority gates: V1, V2, and V3. So we are going to start from V1 and V2 that represent level 0 because they are closer to the input, and after being done with level 1, we will go to level with level 0. We will go to level 1 where we find the next majority operation. In this case is represented by this B3. So first of all, we start with the we start with B1, the first of the nodes, the first of the majority gates, and as you see, it has 3 inputs: A or the negated A, C in, and V. We are going to start first allocating A, and then we will allocate the next one, that is CE. What is what we have to do every time we want to allocate an operand? The first of all is assigning the corresponding operand to one of the 3 rows that we have in the among the designated rows. In this case, we are considering 4 rows T0 to T3 that are designated rows, and we have 2 more that are also designated, are also compute rows, but in this case they are rows of dual contact cells. So one thing we do here, because A needs to be inverted because before executing B1, because before executing the majority operation, what we do is allocating A to the DCC0, because this way we can obtain its inverted value, right? And then we go to the next operand, that in this case is CIN. And then we check another free row. In this case, we assign T0, as you can see. And then we go to the next operand of B1, which is B, and we again go and get a free row. The algorithm finds a new free row. In this case is T1. And this way we have already assigned the 3 inputs of this majority operation B1. We have assigned the 3 inputs to 3 different rows that were available, were free. And we can continue then with the next node. In this case is B2. We are still in level 0. And also we say that we are in phase 0 of the algorithm. We say that we are in phase 0 of the algorithm because we still have some free rows that we can assign to the operands of B2. At the point where we run out of free rows, we will move to phase 1, as we will see. But anyway, first thing is to assign A as well, and we do this to T2, and then we will, actually you can see it here because we still have 2 free rows. We assign CIN to T3 and B to DCC1, and then we move to the next level, that is level 1, which is composed by where we find V3, we find this majority operator that takes the 2 outputs, out 0 and out 1, that come from the previous level, from V1 and V2, and also the third input, that is A in this case. So first thing to do here is to allocate out 1 that is coming from V1, but because it's coming from V1, we know where it is already allocated, right? Remember that after we execute V1, we execute this majority operation, we will have the majority resolved in the 3 rows, and in particular, one of the 3 rows is T0. So we are going to take out 1 from T0. Yeah, and at this point we ran out of free rows, so this means that we have to go to phase 1, and in phase 1 we continue assigning operands to the rows. In this case, operand A goes to T1, and the operand out 2, which is the output from V2, is taken from one of the rows that are used in the operation of V2. In this case is DCC1. But anyway, as you see, this is one example of how the allocation algorithm assigns rows to operands, or assigns operands to rows in order to decide on this and be able to go to the second task, that is generating the microprogram. So now that we have assigned the rows to operands, we can generate the microprogram. And to do so, we have to check what was the allocation that we made before, and based on that, define or decide what's the what's the sequence of DRAM commands that we will need. So for example, if we have A, B, and C in some data rows, the first thing that we will have to do is to copy these 3 rows to reserve rows, to compute rows that we are where we can activate 3 rows at the same time and execute the majority operation. After performing these 3 copies, we can execute the majority operation by issuing an activate and then one pre-chart, and finally we may want to copy the output to some destination row among the data rows of the subarray. right? So this is the initial microprogram, and we can later optimize this initial microprogram. There are different ways or different techniques that we can apply for the optimization of the microprogram. One thing that we can do is coalescing row copies. So in some cases, we are going to need the same operand in multiple times, right? So actually, if you remember, let me very quickly go to the figure here. If you remember this graph here, we see two vertices or two majority operations, V1 and V2, and both of them are using the same inputs, right? A, C in, and V. So the good thing of row clone is that we can copy one single row to multiple rows as well. And the idea, so the way to do that is, remember in row clone, we first activate the source row, we then activate the destination row. So what we can do is activating the source row. And when it comes to activating the destination row, instead of activating only one, we can activate 2 or 3. And this way we are doing multiple copies of the same operand. And we are doing what we call coalescing the copies. Another optimization that we can apply is what we do here as well by merging steps 4 and step 3. In step 4, we are executing the majority operation where we activate 3 rows at the same time with this activate. And then in step 5, we copy the result to the destination row. So one thing we can do here is to merge these two by turning them into an activate pre-charge. The first activate activates the 3 input operands of the majority operation. The second activate activates the destination row in the among the data rows where we will copy the output, right? And by merging these, we are in the end saving DRAM commands and making the execution or making the microprogram more efficient. Now there is one more consideration, is that we are executing bit serial algorithms. So here, for example, you see that this majority gate, this majority operation is taking 3 operands, A, B, and C in, and is generating this output C out. This corresponds to the carry, how to calculate the carry of bit serial adder. But now we have to use this carry for the next bit, right? Imagine that we are operating on 32-bit values. We will start with the least significant bit. We compute the sum and we compute the carry for the least significant bit. And then we have to move the carry to the next bit, to the let's say bit 1. And then we have to repeat the operations, calculating the sum and calculating the carry for bit 1. And then we go to bit 2 and so on. So in the end, we have to repeat this whole process n times, depending on what's the precision of the values, the data types that we are using, right? So if we are using 8-bit integers, we will repeat this sequence of commands 8 times. If it's 32-bit integers, we will repeat this 32 times. And this is the way that we obtain our final microprogram, right? That we are going to store in memory and eventually load whenever we want to execute one instruction. So this microprogram is stored in a DRAM region, in a reserved DRAM region, and now it's time to add the Sindiram instruction, the new instruction, to the CPU ISA. And the CPU will use it, as we are going to see in step 3, which is the execution according to the microprogram after someone has used the new instruction. This BBUP new is a SIMD instruction used by the programmer in a certain application. And we are going to see what the Sindiram control unit needs to do to execute the microprogram when it receives the new BBUP instruction. The first thing to do, as we'll see, is loading the microprogram. And the second thing is to execute the corresponding sequence of DRAM commands that are each of the micro operations of the microprogram that we generated in step 2. But let's take a closer look at what the Sindiram control unit does. First of all, let me clarify that the Sindiram control unit is an extension to the memory controller. So whatever you see here is connected to the memory controller, as you can see here on this right part of the figure. And we are going to see step by step what the Sindiram control unit needs to do. First of all, it receives from the CPU the instruction, the new, the BBOP instruction that is going to be executed in DRAM. And so essentially the CPU decodes a new instruction, sees that this instruction is a BBOP, and sends it to the Sindiram control unit for its execution. And we have here first have FIFO to store all these BBOPs that are coming from the CPU and to start the execution of each of them one by one. In the second step, the BBOP is decoded by this Sindiram control unit, and this means that the corresponding microprogram is searched here in the microprogram scratchpad, which is this is an SRAM-based memory that is inside the Sindiram control unit. If it doesn't reside here, we can go to the main memory. We can go to DRAM to bring the whole microprogram here. Second thing is to set this loop counter, because we will have to repeat these Sindiram the sequence of commands multiple times, not only because the precision of bits, precision of the elements that we are using in computation is n, for example, 32 bits, but also because the operation might apply to whatever we have stored in multiple subarrays. In the end, the BBOP takes one or two source addresses, one destination address, and one size, which is the size of the array that we are operating on. This may be 100,000 elements, millions of elements, maybe. And if that's the case, then it expands these source and destination arrays span more than one subarray, right? And if they span more than one subarray, the memory controller will have to issue commands to multiple subarrays, right? So that's essentially the idea of using this loop counter to keep control of what are the different subarrays that we have to operate on and how many times we have to repeat this process. And yeah, the last thing in this second step is to copy source and destinations and the element size as well to this register addressing unit. The element size is important because this register addressing unit will take care of how many times this micro op memory needs to, so this this microprogram that is stored in this micro op memory needs to be repeated depending on what's the precision of the data types that we are using. And that's so in the third step, what we do is copying the microprogram to the micro memory for the execution to start. Observe that next to the micro memory, we have also this microprogram counter that it's pointing to the next micro operation to execute. And these micro operations, remember, are the activate or pre-charge commands that we will send to the memory controller for it to send them to the DRAM chips. So that's what we do in this step 5. We have the micro processing FSM finite state machine that is checking what's the next micro operation to execute and sending that information to the memory controller for the memory controller to issue the corresponding commands. In step 6, when done is found in the program. So at the end of this microprogram, we have this done operation, meaning that we are done with the Sindiram operation, and now it's time to decrement this loop counter, go to another subarray for execution, and yeah, so the source and destination addresses will be shifted as needed here in this register addressing unit. And finally, in the step 7, in the last step, is when the loop counter is equal 0, which means that we are done. We can finish. We have finished the execution of the BBOP, and then we notify the BBOP FIFO for the and DQ from this FIFO the next BBOP for its execution. Okay, I don't know if you guys have any questions. If not, the 3 steps already covered, we are now going to very quickly discuss the system integration, and then we will go to the evaluation of Sindiram, and you will see the comparison to CPU and GPU. So all these system integration issues are completely covered in the paper. As you can see, I'm not going to discuss all of them today, but I'm going to discuss 2 of them that are really important. The first one is maybe and will answer one of the questions that you may be asking yourselves, is how to transpose the data. Remember that in DRAM, conventionally, we have data stored in a horizontal manner. So the bits from the same word are in different bit lines, but this is not the way that Sindiram operates. Sindiram takes advantage of the vertical data layout, and this way we can have as many SIMD lanes as we have bit lines in each subarray. So now the question is, how do we change the layout from horizontal to vertical, right? Because in the end, the rest of the system, the CPU, the cache hierarchy of the CPU expects data to be laid out horizontally, right? So in the end, what we have to do is changing the layout when we go from CPU to memory, or when we go from memory from Sindiram to the CPU. To do so, we design a transposition unit that is going to be placed between the last level cache and the memory controller. And this transposition unit has an object tracker to keep track of all the arrays that are, or all objects that are going to be operated on by Sindiram. And then it has the corresponding logic and corresponding and necessary buffers to perform the horizontal to vertical transposition when we copy something from the last level cache to the memory controller and to DRAM. And on the other side, we also have the corresponding transpose buffer and corresponding logic to transpose whatever comes from DRAM and through the memory controller, and is going to be written into the last level cache. So here we have horizontal layout, here we have vertical layout. The transposition unit moves data from the horizontal to vertical layout in this part here, and from the vertical to the horizontal layout in this side here. And this a transposition unit is relatively low area cost and also low impact on the throughput of the Sindiram operations. And you can find more details in the paper. And the second thing that I wanted to talk about regarding the system integration is how to program this new system, how to use the Sindiram ISA extensions, and how the programmer can use them, right? Or a compiler can use them. There are several instructions. I mean, the instructions that we need for sure. The first one is this bbop trans init, that in the end, it's useful to indicate when a specific object in memory is going to be operated on by Sindiram. It's going to be used by the processing using DRAM engine in the end. And that's important because it's the way for the object tracker that resides in the transposition unit to identify when something needs to be transposed. Some cache lines that belong to some array need to be transposed when we are reading them from the CPU, or when we are writing them from the CPU to memory. Then we have different new instructions. These are the new instructions that we can create with new instruction codes. But here you can see like the format. It might be 1 input or 2 input. In this case, we only have 1 source. In this other case, we have 2 sources. Size is the size of the arrays that we operate on, and N is the precision of the elements that we are working on, either 8 bits, either 16 bits, or either 32 bits. And then we also have a predication instruction, this bbop if else, that allows us to implement predication in Sindiram and implement, for example, if else statement and perform the corresponding operation for the corresponding path. And we are going to see an example of that, by the way. So here you have the let's say C code that we will need to execute to perform some vector addition or subtraction, but depending on the predicate. Here we have some condition. If AI is greater than certain, say, auxiliary array pred I, then this condition is true. If not, the condition is false. And if the condition is true, we perform the vector addition. If the condition is false, then we perform the vector subtraction, as you see, or the element-wise subtraction in this case. So this program compiles to this other program that, or translates to this other program that uses Sindiram operations, and we are going to present them one by one. So very first thing to do is, because we are going to operate on A, B, and C inside memory, we need to mark them as Sindiram objects, right? For the object tracker to identify them. So that's what we do this with this BBOP transposition init. Next thing to do is to perform or execute this BBOP add. This is one new instruction that we have incorporated to our instruction set, and now it can be used by the CPU. When the CPU finds this opcode, it will send it to the Sindiram control unit for its execution, as we just discussed before. And here with this BBOP add, what we are doing is adding the elements of A, the elements of B, and storing the result in the array C. In the array D. The other thing that we do is executing the subtraction in the other part of the if-else statement. So here we subtract A and B elements and store the result in C. Then we will have to, we check the condition. So in this case, we compare the elements of A to the elements of the auxiliary array pred, and store the results in F. In the end, this F is kind of a is going to be kind of a bit mask, right? It's a Boolean, so it's an array of Boolean values that is either true or false, depending on whether the condition is true or false. And in that case, we will execute the addition or the subtraction. And that's what we do, or after having executed the addition and the subtraction with the predication instruction, this BBOP if else, what we do is that depending on the Boolean values that we have in F, we will copy in C the corresponding element of D or the corresponding element of E that were previously calculated in these instructions in lines 13 and 14. So that's how we can make use of predication. And here you have a simple example of how to use Sindiram operations in our program. Okay, you can find many more details in the paper about how to handle page faults, the limited subarray size, security implications, and so on. The paper is available at our website, and you can also find a version in archive. And finally, let's go to the evaluation. In the end, this is going to be quick, even though it's for sure important. Comparing to CPU to GPU, we are comparing to a state-of-the-art processor-centric systems with CPUs and GPUs, and we also compare to another state-of-the-art processing using DRAM mechanism, that is Ambit. Is the first work that proposed this way of doing processing using DRAM, and we have made use of the majority operations proposed by Ambit, but instead of using and, or, and not for the execution of instructions, we are going to use majority and not, as we have seen in Sindiram. We have evaluated three different configurations of Sindiram. The first one is a single bank, second one is 4 banks, and the third one is 16 banks. It's important to understand that we exploit bank level parallelism here. So that's why we can show results with up to 16 banks, and maybe we could even more if we have more banks in the system. We have evaluated 16 complex in DRAM operations, including absolute value, addition, subtraction, bit count, equality, greater than equal, predication, ReLU, and or an XOR reduction and multiplication and division, and also 7 real-world applications. Let's take a look first at the results throughput analysis. Here we are presenting giga operations per second. We show normalized throughput with respect to the CPU. This is the speed up that we get, or the throughput improvement that we get with one bank with respect to the CPU is already 5.5 times faster. We can multiply these by the corresponding number of banks that we are using, up to 16 in our experiments. And here you see also the comparison to GPU. Observe that with 16 banks, in these 16 Sindiram operations, we are almost 6 times faster than a high-end and state-of-the-art GPU, and also outperforming Ambit as well. So Sindiram outperforms significantly the baselines. In terms of energy, we also see very good improvements in the energy saving, in the energy efficiency, significant energy savings with respect to CPU, GPU, and also with respect of Ambit. So Sindiram is more energy efficient. And then here you see the average speed up with respect to CPU so the average speed up with respect to the corresponding baseline of the 3 versions of Sindiram. So here you see the comparison with respect to CPU for the 7 real-world applications. This is the comparison to the GPU for the 7 applications, and this is the comparison to Ambit. So also very nice and promising results with respect to the 3 baselines. And you can find many more details about this work in the paper, and analysis about reliability, for example, the fact that the size of DRAM and the size of the DRAM cells reduces the generation after generation, makes the system, makes this kind of proposal less reliable, but still we show some promising reliability results in the paper, and also other analyses like data movement overhead, transposition overhead, area overhead, etc. And this is essentially the whole story. We have presented Sindiram, an end-to-end processing using DRAM framework that provides all the elements that you need to make use of processing using DRAM, a programming interface, an ISA or the ISA extensions that we can create by employing the 3-step framework, and the hardware support for efficiently computing complex operations, providing the ability to implement new operations that as desired, using the massive parallelism that DRAM has, essentially using each bit line as a SIMD lane. We have shown very nice and promising results with respect to CPU, GPU, and also with respect to Ambit. That was the state-of-the-art processing using DRAM mechanism that we have considered. And yeah, as I said, it's a promising solution, a promising framework to ease the adoption of processing using DRAM architectures and improve the performance and efficiency of these architectures significantly. So this is all with respect to Sindiram. Guys, let me know if you have any questions. In the meantime, I'm going to check the YouTube chat. Yeah, and yeah, we got one question, but we already answered it. The raw numbers of the Sindiram that I showed, I would refer to the paper if you eventually need more information, something that is not in the paper, and you have still questions about our work. Please don't hesitate to contact by email, and we will try to help as much as we can. Okay, I think that's all from my side. I don't see any additional questions in the YouTube chat. You guys, let me know if you have something else. If you don't, I think we are done for today. Thank you very much for your attention as usual, and I hope to see you all next Tuesday. Bye-bye.